Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 36. Today we will expand upon the design of the first amplifier topology we saw in using CMOS devices, namely the common source amplifier. So before we go there, let's take a look at what we covered last time in studying CMOS technology and amplifiers. We saw that in order to build both NMOS and PMOS devices on the same wafer, on the same substrate, we start out with a p-type wafer. So we have p-doping in the substrate. And then we build the NMOS device, as shown here, using N pluses for the source and drain. And to accommodate the PMOS device, we go ahead and implant or build an N-well. An N-well is a type of is a region that has N-type doping, and then on top of that we build the PMOS device. So in a sense, this is a local N-type substrate that we have created, and these two together now allow us to build both NMOS and PMOS devices and use them in our circuit designs. All right, then we moved on to CMOS amplifiers, and we saw that after many trials and tribulations, we eventually arrived at this topology. We saw the evolution of this topology, where we started thinking about using a simple voltage-controlled or voltage-dependent current source, and gradually going to a MOSFET, adding bias, etc., and eventually we got here. We saw that we prefer to take the output between the drain and this common rail, which we call the ground, and this circuit is called a common source topology. The input is applied to the gate and the output is applied to the drain, as is sensed at the drain. And the source can be considered common to the input port and the output port, and that's why we call it a common source topology. But that's a minor detail. All right, to calculate how much gain this circuit can provide, we replaced all of the devices in here with a small signal model. For example, we saw that the constant voltages V0 and V1 do not change with time. Their change is 0, so they will be replaced by 0 voltage sources, namely short circuits. And after analyzing the circuit, we saw that the voltage gain was equal to minus GM of the device times RD. So we're going to start from here today and develop further and understand some other properties of this type of amplifier. And in fact, we will also look at some variants of this amplifier. So we'll go over some examples, some numerical examples, just to get warmed up. Then we'll include channel length modulation, which we had neglected there. And then we'll look at some variants of the common source topology. All right. So let me talk about a notation that we will be using to simplify our circuits. Let's see. When we have a circuit like this, sometimes we don't want to draw everything in here for simplicity. So we would like to have some shorthand notation for various devices in here. So what we will try to do is, for example, let me change the pen to blue. So we'll talk about some simplifications. Okay, so oftentimes we draw the circuit as shown down here. We have our MOSFET along with the input. So the input consists of a microphone and a bias voltage. And we call this common line here the ground. The ground. And sometimes we don't even want to draw one straight line, one continuous line for all of these. So we just draw a ground symbol here. Similarly for the source, because it's connected to ground, we draw a ground symbol here. And then the resistor goes to RD, the drain goes to RD, and then RD connects to a battery. And this is our power supply, and we really don't want to draw it every time. So we will draw a thicker line up here You can call it a rail, a supply rail, and we write V1 here. Okay, V1. Now, when I write V1 here, I hope there's no confusion. What this really means is that there is a battery connected between this point and ground, this common rail here. But we just didn't draw the battery. That's all it means. And you can see that these ground points are also drawn separately, even though in real life, they're all connected by a single wire. All right. In practice, our notation also changes a little bit. Instead of V1, which doesn't have much meaning, we will call this VDD. VDD. And VDD from now on stands for the power supply voltage and nothing else. So anytime we hear VDD, we know exactly where it is. If we hear V1, we don't know. V1 could be any voltage anywhere. AC, DC, small signal, large signal. But VDD always denotes the power supply is a constant value and is connected to the positive end of all of these devices. All right, we have a bias here. For now, we'll just call it V0. We'll keep it like that. And this is the simplified version of that circuit. Everything that we have here in practice, but it's just simplified for our drawing purposes. All right, now the output, we said, was taken from the drain with respect to ground, if you remember. We will also simplify that. We will just draw a line from here outward, and we say V out. That might be a little strange because we cannot associate a voltage to a node by itself. A voltage is always measured between one node and another node. But this just means that this V out is a voltage that is measured between this point and ground, this common rail here. But we just didn't draw it. That's all. So you should not assume that V out is one node with respect to nothing. It's always with respect to something. Okay, so that is the general simplified circuit that we will use from now on in our schematics, and I hope that you will not be confused by it. Okay, so let's move on to the voltage gain that we just found. So we found that if lambda equals 0, the voltage gain is equal to minus GM RD. And we would like to verbalize this result, say it in words, because sometimes saying it and memorizing it in words will help us with more complex circuits in the future. So we will write this as equal to minus GM. GM is the transconductance of this guy here, multiplied by RD is the total resistance that is tied between the collector, between the drain and this point. Now, if you remember, this point was the AC ground in the small signal model. In the small signal model, we shorted this to ground because there was no, the battery became a short circuit here. And that's what we call an AC ground. DC-wise is not ground. It has some voltage on it, maybe 2 volts or 1 volt. But AC-wise, from a small signal point of view, it is 0. So we say the voltage gain is equal to minus GM times the total resistance tied from drain to AC ground. AC ground means all grounds that we have. Some of the grounds are hardwired. They're already there. For example, this is a hardwired ground. We had it from the beginning. But some grounds are AC ground, meaning that they did not appear in the original circuit. But when we drove the small signal model, we ended up grounding this top terminal, if you remember from the last lecture. And that ground is called an AC ground because its voltage does not change with time. It has a DC voltage, some amount, 2 volts, but it doesn't change with time, so it's called AC ground. And what we see here, RD, is all of the resistance. Now in this simple case, there's just one resistor, not a big deal, but as the circuits become more complex, we want to remember this verbalization of the result. Okay, so what this means is that if I come along and add another resistor from here to here and call it R2, you know what to do. You say, well, the total resistance tied between drain and AC ground is RD in parallel with R2. So this turns from RD to RD in parallel with R2, as an example, right? So, okay, so no problem there. Now, what if I tie yet another resistor? Let's change the color to brown. From here to ground. And let's call this R3. Can I predict the gain with all of these resistors present? Yes. From the drain node, so there's a dot here, from the drain node, we have RD to ground, AC ground. R2 to ground, AC ground. R3 to ground, a real ground. They're all grounds. And they're all in parallel. You can see that they all share the terminals here, and they all share the terminals here, because this point and this point will be one node in the small signal model. So in that case, this would be also in parallel with R3. And then we have this whole thing inside square brackets. Okay? All right, so you don't necessarily design a circuit like this, but this is just to show you that once we have this picture in our mind, we can readily write the voltage gain for any circuit like that. Very well. Let's go ahead and look at some numerical examples just to see how all of this comes together. So I have a circuit, this circuit, with some values, and I would like to analyze it. So here's our circuit. And then I don't bother drawing VDD, the supply battery, and I have RD here. We call this M1, transistor M1, and this voltage is V0. The output is taken from here, and the input, the signal is applied from here to here. That's the microphone signal, for example. And we would like to find the various parameters of the circuit. Now what we know are the following. I have chosen RD to be 3 kilo ohms. So this is 3 kilo ohms. And for this device, I have chosen it's W over L to be 10. Now, we often use this in our examples. It doesn't mean it has to be 10. It can be 5, it can be 1, it can be 100, depending on what you're trying to do. But just as an example. All right. Then for the MOSFET, we also need some parameters. We need to know mu and Cox. So I'm assuming 100 microamps per volt squared. And the threshold voltage is, I have assumed 0.5 volts as usual. And for now, we assume lambda is 0. Okay. I have chosen for V0 a voltage of 1.2 volts. So that's 1.2 volts. And for the supply, I have chosen 2 volts. So 2 volts here. So anytime this picture is not quite clear, you go back here. You remember that, okay, this is 2 volts from here to here. This is 1.2 volts. That's 3 kilo ohms, etc. All right, we would like to analyze this amplifier. And if you remember from the procedure from last time, analysis or design, the first task that we have to embark upon is to calculate the bias conditions. Now here, we already have, for example, the gate source voltage under bias conditions, meaning without the signal. If the microphone doesn't produce any signal, this voltage is 0. So the gate source voltage of the device is equal to V0, equal to 1.2 volts. So we already have the gate source voltage. That's the bias voltage for the gate source. Okay, what else do we need to know? Well, we need to know the drain source voltage, because we have to make sure it's in saturation. With this between gate source and drain source, that we know whether it's in saturation or not. So we have to calculate that. And once we know it's in saturation, we go ahead and use the correct equation. 1/2 of mu n C ox W over L times VGS minus VTH squared. And using that, we can find the bias current. So now, once we have the bias voltages and the bias current, we can find the small signal parameters, GM and maybe RO. In this case, RO is infinity, but in other cases it may not be. Once we have the small signal parameters, we can go ahead and find the voltage gain. Okay, so that's the procedure. All right, so let's begin with all the bias calculations. Okay, so we start with the step number 1, bias calculations. Well, we know that VGS in the absence of a signal is 1.2 volts. So that's good. How much is VDS? Well, we don't know. What we know is that this resistor is 3 kilo ohms. But to determine this voltage, I need to know the voltage drop across the resistor. If you remember last time we wrote a KVL, we said this voltage is equal to this voltage plus this voltage. So to find VDS, I need to know the voltage across the resistor. But the voltage across the resistor is determined by the bias current, and I don't have the current yet. So what do? I don't know if it's in saturation. So can I use the saturation equation for the current? Well, we will go ahead and use that. We'll use the saturation current equation. And at the end, we have to check. If at the end it turns out that it is not in saturation, then we have to go back and use the triode region equation. But let's proceed and see what happens. So we write here in big letters so that we remember later, assume saturation region. So that's a big assumption, and later on we have to come back and check to make sure that it is correct. All right, so then I say ID is equal to 1/2 of mu n C ox W over L VGS minus VTH squared. I don't have 1 plus lambda VDS because lambda is 0. Okay, so now because I have VGS, VTH, W over L, mu and C ox, I can find ID. And that ID is equal to 245 microamps. So this is equal to 245 microamps. Okay, so the first thing we have to do is to make sure that the device is in saturation. So let's try that. We will write VDS, maybe it's easier to see here, VDS is equal to V1 minus RD ID. Right? This voltage minus this voltage is equal to this voltage. So we write VDS is equal to V1 minus ID RD. And remember, this is still just for bias calculation, so there are no signals coming in. We're just looking at the effect of VGS, which creates a current, and the effect of a current as it generates a voltage across RD, and then how much voltage is left for drain source of M1. Okay, so sorry, this is VDD in our example. This from now on we call it VDD. So that's 2 volts minus 245 microamps times 3 kilo ohms. And of course you should be careful with the units, and that will give us a VDS of 0.53 volts. Let's see. I think that's what I got. 0.53 volts. Let's see. 0.7, 1.265. No, I got 1.265 volts. Okay, so that's equal to 1.265 volts. Okay, so here's what we have. Assuming the device is in saturation, we have a certain current. And again, using that assumption, and using this current, we can find VDS. Now, is the result agreeable with our original assumption? Well, VDS is 1.265 volts. VGS is 1.2 volts. That's great, because we know that this device is saturation even if the drain comes below the gate by as much as one threshold. In this case, the drain is not even below the gate, so the device is in saturation. Okay, so no problem. We are in saturation. We're good to go. Okay, so we have found the bias voltages and the bias current of the device. We're done with bias calculations. Now we can go ahead and find the small signal parameters, in this case only GM, and then from there calculate the voltage gain. All right, so GM, so in this step number 2, we calculate small signal parameters. You realize that to get here, we do need to calculate the bias values, right? Because the small signal parameters are dependent upon the bias values. So which equation do I use for GM? We have 3 of them. It doesn't matter. We can use any of the 3. I will use this one, 2ID over VGS minus VTH. ID is 245 microamps. VGS minus VTH is 1.2 volts minus 0.5, so 0.7 volts. And when we calculate that, GM is equal to 0.7 millisiemens, 0.7 millisiemens, or 1 over 1.43 kilo ohms. I like both versions in terms of Siemens and in terms of ohms because it gives me a better feel for what's going on. When I look at this number, I say that this GM is not very high. It's not a very strong transistor, because I would like to see this on the order of 1 over 100 ohms, 1 over 200 ohms, or even better, meaning a higher amount of GM, so that it would be considered a relatively strong transistor, if you will. We don't really use the term strong transistor in our jargon, but sometimes it's good to think of it that way. Okay, so that's the GM, and now we can calculate the gain. So 3, calculate the gain. So AV is equal to minus GM times the total resistance tied between the drain and AC ground. And that's the only resistor we have, 3 kilo ohms. We don't have anything else. Lambda is 0. So that's equal to GMRD. And that comes out to be minus 2.1. So the gain of the circuit is only 2. It's not a very good amplifier, right? We would expect to have a higher gain. But it just happened that with the choices that we have made here, the gain comes out to be only 2. Okay, but this procedure tells us how to analyze a given circuit and start from its bias conditions and then find its small signal properties. All right, so if the gain is given by GMRD, how do we increase the gain? Well, we have 2 options, increase RD, increase GM, right? Only these 2. So let's pursue the first option of increasing RD and see how that goes. In other words, you design this amplifier, you got a gain of 2. And your boss came back and said, no, that's too much, that's too little, I need a gain of 4. So how do we do that? You say, okay, I will just increase RD by a factor of 2. That will give me a gain of 4. So can we do that? Let's try that. So let me change the color of my pen and see what happens. Okay, so I'll put some dashed lines here. Need to double the gain. So try doubling RD. So we keep everything else the same. The transistor is the same. It has the same W over L, etc. The voltages here are and here, etc. are the same. All we do is increase RD by a factor of 2. So we are at 6 kilo ohms. Okay, so that seems to give us a gain of minus 4.2. which is fine, but we have to be careful. If I increase this resistor by a factor of 2, I need to go back and check my bias conditions. Is the device still healthy? Meaning, is it in saturation? So let's go ahead and do that. Okay, so what could change when we double the resistor? VGS doesn't change. VGS is given by this battery. The microphone doesn't produce any signal. We're good there. But what happens is that if this resistor doubles and the current is still 245 microamps, because we're thinking this equation hasn't changed, then the voltage across this resistor doubles the bias voltage, the DC voltage. If the DC voltage across this resistor doubles and the battery is fixed, so the battery is fixed and this voltage doubles, we end up with less VDS for M1. So as RD increases, and we assume that the current of M1 is constant, then this voltage collapses. So it's possible that doubling RD will actually drive M1 into the triad region. And then we have a problem. So we have to check. All right, no problem. We know what the equation is. So we say if ID, okay, my pen started acting up here. Not here, this one. If ID is still equal to 245 microamps, we have this equation. We have the drain source voltage is equal to VDD, which hasn't changed, still 2 volts, minus RDID. We have assumed ID hasn't changed, but RD has doubled. So let's plug in the numbers here and see what we get. And now we get a VDS of equals to 0.53 volts. So 0.53 volts. Now we have a problem. The drain source voltage is 0.53 volts. The gate source voltage is 1.2 volts. The device is not in saturation, because if I take 1.2 volts and I subtract one threshold from it, I get 0.7 volts. So VDS has to be greater than 0.7 volts, but it's not. So compare this to VGS minus VTH. And we see that that's 0.7 volts, which is greater than VDS. There's an NMOS device, so we are in triad region. So as you can see, we cannot just increase RD, because at some point the device goes into triad region if we keep everything else the same. So it has limitations. Because VDD is limited to, for example, 2 volts, as we increase RD, this difference quickly drops to a small value, and then we have a problem. If VDD were higher, it might be okay. But today's CMOS technology runs from a supply of maybe 1 volt, etc. So it's very hard to do that. And our hands are really tight. We cannot increase RD much to increase the gain. Okay, so that was the issue with increasing RD. Now you say, well, why don't we increase GM? Right? Not RD, just GM. Okay, so let's try that. So try increasing GM in order to increase the gain. Well, GM has 3 expressions. I will write one of the expressions, which is quite helpful in this case to show you what happens. So we know that GM is equal to 2 mu n C ox W over L times ID. Mu n C ox is a given parameter for the technology. We don't have any control over it, so no problem there. We have W over L to play with and ID. So I will draw 2 scenarios. ID goes up or W over L goes up. right? These are the only options we have for increasing GM and hence the voltage gain. Okay, well, if ID goes up, something again goes wrong. Let's go back to this equation. Previously, we attempted to increase RD, and as a result, this difference collapsed, so VDS was too small. This time, we're trying to increase ID. Same problem. If you increase ID, this term increases, this term decreases, VDS decreases, we go into triad region. So again, ID has a certain limit. For a given amount of RD, ID has a certain limit. We can't do much. So let me write that down here. Eventually, triode. Okay, you know what that means. So as ID increases and everything else remains the same, eventually we go into triode region. And that's because as I increase more the current drawn from this resistor, the voltage across this resistor increases, and the total voltage is fixed. That's the supply voltage. So VDS keeps coming down, right? VDS keeps coming down, and eventually it's too low. We'll go into triad region. Okay, how about the second option, W over L? So let's assume that the drain current is constant, but we make the device wider. That's possible, right? Do you know how to do that? So let's go back to this equation. What I would like to do is keep ID constant, but increase W over L. That's possible provided that I play with VGS minus VTH. So I make W larger, but I reduce VGS minus VTH such that ID is constant. Okay, we can do that. So let's go ahead and do that. We keep ID constant, and we keep making the device wider and wider. So that seems to give us plenty of flexibility. If ID is constant, this VDS is constant, so we're good. We're not collapsing. And it seems that we can increase W over L indefinitely, increase GM indefinitely, and achieve a very high gain. Unfortunately, that's not true. So without going through details in this course, what I will show you is the final bound on this GM as we make W over L larger and larger. So we did not cover this in this course, but just for your curiosity, if W over L becomes sufficiently large, this equation is no longer valid. Okay, in fact, we have to change it. The GM becomes approximately equal to ID over 1.5 times VT. VT, if you remember from the exponential equation we had for diodes, is equal to KT over Q and is equal to 26 millivolts at the room temperature. So it's very strange, that this equation is like this for moderate values of W over L, etc. But as W over L becomes very large, W becomes very large, then the equation completely changes. All right, this is related to what we call sub-threshold conduction, and it's beyond the scope of this course. But you should know that for a MOSFET, if we keep ID constant and increase W over L, GM does not go up indefinitely. It is eventually limited by this. So if ID is 245 microamps and VT is 26 millivolts, you can calculate how much GM we can get eventually. We cannot exceed this, so the gain of the circuit will be bounded by some amount, right? It cannot go higher than that. So this is the upper bound on GM as W over L becomes very large. Okay? So just keep it like that. In more advanced courses, you will play with these and you will see how they can be used to calculate the behavior of these circuits. All right, today in Frontiers in Electronics, we will talk about the future of circuits. Having sat through all these videos, you might be asking yourself, circuits have been around, electronic circuits have been around for about 100 years. So isn't this stuff old now? Isn't this stuff mature and well established? If I go out, can I find a job in electronics, in circuits, in circuit design? Maybe everything that needs to be invented in circuits has already been invented. So is there any future in this? Or is electronics like the steel industry? The steel industry has been mature for many decades. You can't really have any more innovations in building steel doors and steel frames. Similarly, are we done with innovations in electronics, electronic circuits? And the answer is no, we are not done. We have a long way to go. Now, as an example, to show you why electronics is still challenging, interesting, and exciting, I would like to take you to the a program of a conference in our field, which we call the International Solid-State Circuit Conference. This conference is held every year in February in San Francisco, and it attracts about 3,000 people from industry and from universities. So these 3,000 people come just to learn about circuits. That's it. All come about to learn about circuits. So that should tell you right away that circuits is still very well alive and very exciting and very prosperous. Otherwise, 3,000 people would not come and pay a large, high registration fee to attend this conference. But let me just take you through some of the highlights of what appears in this conference, for example, for 1 year, to see what's going on. So there are many sessions of papers. There are lots of papers that people present, and I just want to show you some of them. Image sensors and technology. So this is all about a single chip eye tracking sensor, a sensor that can track our eye movements. Great for people who have lost the ability to speak or have any sort of bodily movement, so that's great. Filters and amplifiers. Remember we talked about amplifiers so far? We also talk about filters later, all of these. Microprocessors. Microprocessors are what we use in pretty much any device these days. These are devices having many components in them. They have billions of transistors. Then high-speed transceivers. High-speed transceivers are circuits operating at tens of gigabits per second. And you can see that there are many different papers on this. Then we have, go down here, ultra-wideband. Ultra-wideband is a type of wireless communication. Then we have electronics for life sciences. So again, for example, various wireless body sensor networks, many different types. Then we have medical and displays. So we have things related to brain, to heart, etc. Then we have millimeter wave and phased arrays. Millimeter waves are frequencies above 30 gigahertz, and they have many interesting applications. These are all circuits related to these types of frequencies. Then we have cellular transceivers. Cellular means your cell phone. These are transceivers, wireless transceivers that go into your cell phone. So we have many papers on these. Far from saturation, far from being mature, because there's still a great deal of work to be done on this stuff. And then we have optical communications. And then we have high efficiency data converters. Data converters mean they convert analog to digital or vice versa. And then we have mobile processing. We have graphics and DRAMs. And then we have low power digital. We have wideband receivers. We have PLLs and oscillators. Remember we talked about oscillators? We have oscillators in the Bluetooth system, in the radar system, etc. There's still a lot of work on oscillators. Oscillators have been around for 100 years, but we still work on them because we want to improve their performance. Then we have wireless LAN, like Wi-Fi. We're still working on Wi-Fi, even though Wi-Fi has been around for 10, 15 years. SRAMs, memories, and many other ones. Non-volatile memory, analog power techniques, building blocks for high-speed transceivers, wireless frequency generation. All of these are topics that are discussed in great detail at the level of state of the art in these sessions. Interestingly, of some 30 sessions that we have here, about 5 or 6 of them are pure digital. We have digital techniques, microprocessors, memories, and the rest of them are more or less analog. So analog has a tremendous amount of application in these different papers. So this is to show you that the circuit design community is still thriving and has a bright future. I will talk more about these as we go along. All right, so now that we have analyzed a simple example of a common source stage, let's go ahead and include the channel length modulation effect in the amplifier and see if the results change. We saw that the gain of the circuit was given by minus GM times RD, RD representing the total resistance tied between the drain and AC ground. Okay, so well, how do we do that? Not that difficult. We go back to our circuit, draw the small signal model, include the RO in the transistor model, and then calculate. So that should be easy. All right, so here's what we have. So again, we draw the small signal model of the circuit. Let me draw the overall circuit before we attempt that. It's always good to remember what the circuit looks like. So this is VDD. This is RD, and we have V0 here, and then we have V out here. So the small signal model is constructed starting from the left. The microphone is replaced by a simple time-varying voltage source, so that doesn't get set to 0 because it varies with time. So here's our microphone signal, which we call V in. And this battery goes to 0 because its change with time is 0. For the MOSFET, we have to have a small signal model, assuming, of course, that the signal that's coming in from the microphone is small. And now we have the source. The source goes to ground, so that's good. This voltage-dependent current source is given by GMV1. And then we have to add RO to represent the channel length modulation effect. So we have RO here. And we also have RD. RD goes from here to AC ground because the battery becomes a ground, becomes equal to 0 because it doesn't change with time. And this is V out. V out, again, is measured from here to ground, right? It's a voltage between these two nodes, which we just write it like that for simplicity. Our objective is to find V out over V in. Okay. Well, I can write all the equations we did before, not a big deal, but I'm too lazy. I really don't want to do that. So I go back to our verbalization on the previous page and say, can I just use that instead of writing equations? I said the gain is equal to minus GM times the total resistance tied between the drain and AC ground. All right. So if I just find the total resistance between the drain and AC ground, I just put it here and multiply by minus GM. I just have to be careful how I find that total resistance. So let's do that. We don't really want to write equations unless we have to, right? Because we're hoping that we are building up these skills so that when we get to larger circuits and writing equations becomes prohibitive, we can at least have some estimate of the behavior of the circuit. Okay, all right, so let's sit at the drain right here and ask ourselves, what is the total resistance tied between the drain and ground, AC ground? This has only AC ground, or well, this has grounds in it, so we just look at the grounds. Okay, so of course we have RD from here to ground, but then we also have RO from here to ground. You see, RO is connected between this node and ground. It just happens that one of these is real ground, the other one is AC ground, but they are still ground because none of them change with time. So I write AV is equal to minus GM times the total resistance tied between the drain and AC ground. So that's RD in parallel with RO. They share a terminal here, they share a terminal here. So that would be RD in parallel with RO. And that's it. We don't need to write equations for the circuit. In fact, we didn't even need to draw this small signal model. If you looked at this circuit, we could say the same thing. Because in cases like this, what I do is I change the color of my pen so that I don't get confused. And I say, well, this transistor has an internal RO in it, right? So I will draw that explicitly here, RO. Now that may not be quite legal because RO belongs to the small signal model of the device. This is not really the small signal model, all that. But without showing anybody, I'll just do it like this in my head. I say, oh, there's an RO from drain to source. I'll just draw it like this. I take it out of the transistor and draw it here. And I say, well, from the drain, I have RD to AC ground and RO to AC ground. So, boom, that's what we get. Okay, so we don't even have to draw this. It's important to remember that RO is connected between drain and source of the device, right? Not from the drain to any ground, right? It's always connected between drain and source. Now it just happens that source is grounded in the circuit, so RO is exactly in parallel with RD. Okay, so that was very easy, right? We just found that. Let's look at an example. This equation says something interesting. This equation says that in order to, first of all, channel length modulation does reduce the gain. Previously we had GM-RD, now we have GM-RD in parallel with RO. Anytime two resistors go in parallel, the net result is less than either of those resistors. So the gain has dropped. This also says that if you want to maximize the gain, you can maximize RO or RD or both, and of course GM to some extent. So maybe what I can do is find a way to replace RD with infinity. What does it mean, replace RD with infinity? Well, here's what I'm thinking. Here's our little circuit as usual. We have a microphone. I draw this microphone every time just so that we still feel comfortable with the circuit, but eventually we don't need a microphone. Right? Obviously, you're not amplifying a microphone signal all the time, but I just draw it here for the purpose of clarity. Okay. All right, I'm trying to replace this RD with infinity. Does it mean an open circuit? Well, here's the power supply, right? VDD. And I'm thinking if I maximize RD, then I maximize AV. So why don't we just replace RD with infinity, which means an open circuit. But an open circuit would be a problem, right? See, it's an open circuit here. Because if it's really an open circuit, no bias current can flow from the battery through the device to go to ground. So this device won't have any bias current. If it doesn't have a bias current, its VDS will be 0. If VDS is 0, then we are in deep triad region, so we don't have any gain. So that's no good. We do need a bias current. We need to operate in saturation and have a bias current for the device to be an amplifying device. So that's the problem. If I open this up so as to achieve RD equals infinity, I also lose the bias current. So what I'm looking for is something that goes between here and here that provides a bias current. Let's say 1 milliamp or 245 microns as we saw before. But as far as the signal is concerned, as far as the signal and small signal analysis is concerned, it's an open circuit. So it's an interesting device. It's a two-terminal device. It does have a constant current through it to provide the bias current of this device. But it's also an open circuit as far as the small signal model is concerned. Fortunately, we know such a device. An ideal current source is exactly that. So we place an ideal current source here. We call it I1. I1 is constant and ideal. So I1 is constant and ideal. So it provides some current, whether it's 1 milliamp or 245 microamps, etc. So this device can be biased up. It's happy. It's in saturation, hopefully, and everything is good. Now, when we draw the small signal model, what do we do? Okay, let's draw it. We start out from the left side. This battery goes to 0. The microphone is replaced by a voltage source because it's time varying. So here's V in. Then we go to the MOSFET. The MOSFET has something like this, RO. This is V1, the GM V1. And now we have to see what goes here. Well, if you remember, we said for small signal analysis, we set anything that doesn't change with time to 0. This current source does not change with time, therefore it's set to 0. A 0 current source is equivalent to an open circuit. So there's nothing connected between here and AC ground. There's nothing connected here, right? That's it. That RD is gone because it's infinity for small signal purposes. So that's V out. We need to find the voltage gain of the circuit. This is a special case of that circuit, right? It's the same circuit except that RD is replaced by an ideal current source. So we can readily find out what the gain is. Just compare these two. What happened? The only difference is that RD has fallen out. RD has become infinity. So we just go to this equation and let RD go to infinity. Infinity in parallel with RO is RO. So AV is equal to minus GMRO. GMRO has a particular significance because it's related to the transistor itself, not what's around it, right? You see, this gain is now given by this transistor. We don't have anything outside, any resistor or anything. So this has a name. We call GMRO the intrinsic gain of the MOS device. And this shows that the maximum voltage gain we can get out of a single transistor is this much. We cannot do better than that because we let RD go to infinity. That's the best we can do. So that's why this has this significance. In today's MOS technologies, GMRO is on the order of 5 to 10. It's not very high. But that's okay. In fact, in many of our calculations, we will assume that GMRO is much greater than 1, which is okay around here, but not a very good assumption here. But we might make that assumption sometimes. Okay, so that was this example. Let's move on to the next case. All right, I would like to talk about another concept that we will need frequently in our circuit analysis and design, and that's the concept of port impedances. Now, these are things that you have seen in circuit theory courses, but I just want to give you a quick refresher before we jump into our electronic circuits. So let's talk about concept of port impedance. In this course, we use impedance and resistance interchangeably, even though we know they are not exactly the same. In courses after this course, we will begin to distinguish between resistance and impedance. Okay, so suppose I give you a circuit like this, and it has an input port. A port means there are two nodes to which I can apply, for example, a voltage. So you might call this the input port of the circuit. Here, the input port is between the gate and this point here, right? So if we go back to the original drawing, it might be easier to see it because here we see this is the input port between this point and this point, right? Where everything is coming in. So we call that the input port. So for a port, we can define an impedance. And that impedance is calculated as follows. We do in two steps. Step number one, we kill all the independent sources inside the circuit. By kill, we mean we set them to 0. Every single independent source, voltage source or current source, is set to 0. A voltage source set to 0 becomes a short circuit. A current source set to 0 becomes an open circuit. So I will write here, set all independent sources to 0. So obviously, something like this would not be set to 0. That's a dependent source. But if we have a battery, we have a current source, that sort of thing, constant current source, those all are set to 0. Okay, well, it doesn't have to be constant current source, anything that is independent. All right, so that's the first step. We set all independent sources to 0. In the second step, we go ahead and apply a small signal voltage between these two nodes, Vx. This voltage perhaps creates some sort of current in here, right? And we measure that current, Ix, and we call this Rin, the input impedance, is equal to Vx over Ix. Okay, so let me give you an example. Here's a simple voltage divider that we have seen in basic circuit theory. This is the input port, right? So what is the input impedance of this circuit? No problem, we apply a voltage source here, Vx, and measure this current, Ix. So how much is that? Well, we see that these two resistors are in series. I don't really have to do this calculation. I could, but I can just write Rin is equal to R1 plus R2 because the two resistors are in series. Or if you want, you can calculate that and see. Okay, so that's what we mean by the input impedance of a circuit. Now, we have a similar situation if we are looking at the output of a circuit. So a circuit has a certain output node. So here, for example, this is the output port. This is the output port here, right? And I would like to find the output impedance of a circuit. So here's the picture that we have in that situation. We have an output. Okay? And in the first step, we set all independent sources to 0. So independent, my pen again is crazy. So independent sources set to 0. Everything from here to the left has to be set to 0 if it's independent, it's an independent source. So there's one source that we might forget, and that is this guy here, this voltage source. That's the input voltage source, right? That's the input voltage source coming in. That's also an independent source. So that has to be set to 0, meaning it has to become a short circuit. So we draw a short circuit here to emphasize that even that voltage source has to be set to 0, assuming that the input to the circuit is indeed a voltage source. If it's a current source, it's an open. If it's a voltage source, it's a short circuit. So it's important to remember that. You have some stuff in here, but this is also part of this circuit. So all the independent sources have to be set to 0. All right? This might be reminiscent of Thevenin's theorem, if you remember. Right? To find the Thevenin resistance of a circuit, that's what we did. We set all independent sources to 0, and then we came along and applied a voltage source from outside, called it Vx, and measured the resulting current, and we call that Thevenin resistance. Here we call it output resistance. It's exactly the same thing. So our out equals Vx over Ix. As an example, let's go back to that voltage divider, R1 and R2. And I would like to find the output resistance of this circuit. I have to set all independent sources to 0. If the input here is a voltage source, which is usually the case, I have to set that to 0. It becomes a short circuit. And now I come along. This is inside the black box here, right, with all the stuff. So now I come along and I apply Vx from outside, and I measure Ix. And of course, in this very simple case, I don't have to do much calculation. I can see that R1 and R2 are in parallel. So here, in this example, R out is equal to R1 in parallel with R2. All right, so the concept of port impedance applies to any two nodes that we pick in a circuit. These two nodes, those two nodes, any two nodes in here, you can always perform this test. We set all independent sources to 0, and then we go in, apply our own voltage from outside, and measure the resulting current. That will give us the impedance between those two nodes. Now, why this is important will become clear later, but this is the method that we need to follow every time we are interested in an impedance. Okay, our time is up. Next time we will use these concepts to look at some other types of common source amplifier topologies. I will see you next time.